Let's consider the functions f of x is equal to 2x and h of x is equal to x to the fourth minus x squared plus 2. What I want to look at is, what is the limit as x approaches one of these two functions? So we'll start with f of x. The limit is going to be, well, you can just put 1 in place of x and you get 2. You can do the same thing for h of x. Again, you can just substitute 1 into all the x's and you get 1 to the fourth minus 1 squared plus 2. And this limit is equal to 2 as well. It turns out that the limits are actually the same thing. The squeeze theorem says that if you have a function, and I'll call that function g of x, and you don't have a formula for it, you don't even know what it is, but if you do know that it falls between these two functions, f of x and h of x, so it's, let's say, greater than this function but less than this one, if that's true, you can determine that the limit as x approaches 1 is also 2. It's actually equal to these two things here. Let's use a graph to see why this actually happens. So using the same two functions as on the previous slide, I've now included their graphs. So this thing here, the red one is f, and the blue one is h. And what we figured out on the previous slide is the limit as we approach 1 of both of these is equal to 2. So that's where they actually meet up. What does it mean graphically for a function g to be greater than or equal to f, but also less than or equal to h? I'm going to draw that in here. I'll draw it in like this. So here's my function g. It's definitely lower than h, but it's definitely above f. And I want this to always be true as we're near this spot. If this holds true, the squeeze theorem says that, well, the limits have to match up at this one location because the function is forced between the two graphs. So here, this is my function g. Because the limit of f as we approach 1 is equal to 2, and likewise, because the limit of h as we approach 1 is equal to 2, that forces the limit of g to be 2 as well. So I don't have to know anything about the formula of it. All I need to know is the limit of this and the limit of this and the fact that this function lies between them if we're near this point. Now, it could be that your function g isn't always lower or above one of the functions. Like, this could happen. All that matters is as you approach this point, you have one function that's above, one that's in between, and one that's below. And if they match up at this point, I know what this limit has to be equal to. That is, the limit as x approaches 1 of g of x is equal to 2. So here's the formal statement of the theorem. We assume that f is less than or equal to g is less than or equal to h. And we only need to assume this when x is near the value a that we're taking the limit of. If you know the limit of this is equal to L, and the limit of this is equal to L as well, then the function that falls between them has to have the same limit.